Well, this app helps you to understand what the p-value is. So the p-value is one of the most probably widespread and also most controversial thing in statistics, especially in frequentist statistics. So I'll try to explain what p-value is using an experiment with tossing a coin. Okay. Imagine that we toss a coin, and our null hypothesis is that the proportion of, let's use this as, for example, tails, and these are heads. So the blue are tails and the orange are heads, but I will use the color names instead, right? So the null hypothesis that the proportion of tails, or the blue outcomes, it's 50%. So it means that we have equally likely the tail and the head. So the coin is balanced, right? So this is our null hypothesis, right? And then you can see I tossed my coin 4 times. So my sample size is 4 in this case. And you can see that I indeed got 2 tails and 2 heads, right? So the sample proportion is 50. Now I need to compute a p-value. And now let's recall what p-value is. The definition of the p-value is following. P-value, it's a chance to get a sample as extreme as yours in relation to the null hypothesis, as you have, or maybe even more extreme, assuming that null hypothesis is true. So the null hypothesis is that the proportion is 0.5. My sample has a proportion of 0.5. So let's compute how many outcomes, what's the probability to get a sample as extreme as mine, or even more extreme? Well, first of all, you can see that my sample has exactly the proportion of the population, right? So how often, I will have sample as extreme as mine. So it means that how often I will get sample with proportion 50. These are all possible outcomes. So if you look at these outcomes, you can see I have 6 outcomes where I have 2 tails and 2 heads, but in different sequence, right? So for example, this is tail, tail, head, head, or tail, head, tail, head, tail, head, head, tail, like I have here. So all these outcomes are as extreme as mine. So they have the proportion, exactly the same proportion as I have. So this is 6, right? Now, any outcome in this case, which is different from this one, will be more extreme. Why? Because I believe proportion should be 50, and I got 50. So if I get 25, or if I get, for example, 75, it will be more extreme, right? So therefore, any other outcome will be even more extreme. So I have 10 outcomes where I have even more extreme. So all tails, or all heads, or only one tail, or only one head, and so on and so forth. These all outcomes are even more extreme. Now look, I need to find a chance to get a sample as extreme as mine, and this chances is 6 over 16, because I have 16 outcomes in total if I toss a coin 4 times, right? So these are all outcomes. So as extreme as mine, or even more extreme, assuming the null hypothesis is true. And this is the p-value. So this is a chance to get a sample as extreme as mine, it's 6. This is a chance to get a sample even more extreme, it's 16. And these are all possible outcomes. So 16 out of 16, it's 1. So the p-value is 1. It means that I should accept null hypothesis, because I have no evidence against the null hypothesis. My sample is perfect for this null hypothesis, right? In reality, of course, you will never get 1, because this is a little bit artificial example, because in reality, you deal with continuous values, not just binary outcomes. And you cannot compute number of outcomes for the continuous values, right? So therefore, we need to use distributions to compute the p-values. But this is a little bit artificial example where the number of outcomes is fixed. It's 16. You always have 16 outcomes if you toss coin 4 times. You always have 16 outcomes. And therefore, depending on the null hypothesis, you can compute these p-values directly just by counting outcomes. Let me take a new sample, this one. Now look, it's different situation, right? Because now my sample is extreme. It's not the same as a population, as a null hypothesis. So I have 24% of the tails, of the blue ones, right? So now I can compute a p-value. Is it possible to get this outcome, or even more extreme outcome, although I assume that it should be 50-50? Yes, it's possible, and this is the chance, 62.5%. How I compute it? So once again, what's the definition of p-value? It's a chance to get a sample as extreme as mine or more extreme. My sample is extreme because I don't have 50-50, right? I have 25% of tails. But what will be a sample as extreme as mine? So any sample with 25% of tails or 25% of heads will be as extreme as mine. So these are all possible outcomes where I have 25% of heads or 25% of tails. So I have 8 outcomes in total, right? All these samples are more extreme because here I have 100% of tails or 100% of heads. So these outcomes are even more extreme if you take null hypothesis is true, right? But these outcomes are less extreme. 6 outcomes where we have 50-50, they are less extreme as the one that I observed now. So now the p-value is, it's a chance to get one of these outcomes, it's 8 out of 16, right? Chance to get one of these outcomes, it's 2 out of these 16. So these two both chances, so I sum them up. And then I simply divide to all possible outcomes. So 2 plus 8 divided to 2 plus 8 plus 6, it gives me exactly 62%. And it's pretty large percent. So it means that if I repeat this experiment again, in 62% of the time, 62.5% of the time, my sample will be like this, or maybe even like this. Okay. Now let's talk about tails. So in this case, I have both tails. What it means? It means that I believe it's exactly 50%. So if I have something smaller or larger than value, then it's equally extreme, right? But what if I change the null hypothesis? And now look, my hypothesis is following. It's 50% of more or more. So it means that I expect to see at least 2 of the blues, or maybe 3, or maybe 4, okay? But at least 2. In this case, the direction of extremeness is different, because now, what will be as extreme as mine? You can see I see 25% of the blues, but I expect to see 50 or more. So every time I have 25% of the blues will be extreme. So these are as extreme as mine. What will be even more extreme? When I have no blues at all, right? So 1 blue is extreme because I expect to see 2 or more. So 1 is extreme, and then if I have none of them, it will be even more extreme, right? So again, how to compute p-value? It's a chance to get a sample as extreme as mine, or more extreme, assuming that null hypothesis is true. And that's the chance, right? So I have 4 outcomes as extreme as mine, 1 outcome even more extreme, and I have 16 outcomes in total. And that gives me a p-value of 31.3%, which tells me that if null hypothesis is true, and if I repeat this experiment again, I have 31.3% chance to observe one of these outcomes, or this outcome. So it means that my sample is not that extreme for this population. This outcome is quite possible, is quite likely. So I cannot reject null hypothesis in this case, right? And then if you change the details, you can see that what you had less extreme, now it becomes more extreme. And what you had as more extreme, it becomes less extreme, right? And this is the same. Why? Because now we expect to have 1 or less. So it means that if you have less, it's less extreme. But if you have more of this, it will be more extreme. So in this case, you can see that the p-value is much larger, right? And then we can repeat it for a larger sample size. It gives us possibility to have a little bit more outcomes, a little bit more different proportions, right? So again, in this case, you can see that let me just start with both tails. So I expect to have 3 blues and 3 orange, right? But I got only 1 orange. Is it likely? If null hypothesis is true, how likely I can get this one or even more extreme? Again, the idea is following. First of all, we compute how many outcomes we have as extreme as our. What means as extreme? It means that with 1 orange or 1 blue. So you can see in all these outcomes, I have either 1 blue or 1 orange. I have 12 outcomes in total, which will be as extreme as mine. And 2 will be even more extreme, because in this case, I have only blue or only orange, right? So the chance to get one of these outcomes, you can see 12 plus 2, 24, divided to all possible outcomes, I have like 64 all possible outcomes, right? So the chance is 20%, 22%. So it's quite likely. So in this case, I also cannot reject null hypothesis, because if I repeat this experiment again, and if null hypothesis is true that the coin is balanced, in 22% outcomes, I will have only 1 orange, or no oranges at all, or maybe only 1 blue, or no blues at all. Okay. Again, if I change the tail, it changes the situation a little bit. So now I expect that number of blues should be 50% or more, right? So it means that number of oranges should be also less than 50%. And you can see I have less than 50%. So my sample is actually not that extreme for this null hypothesis. Sample as extreme as mine is a sample with exactly one orange, because now I have one tail hypothesis, right? So only one orange. And then every time I have even more orange values, it will be more extreme sample. And this is less extreme. This is perfect for my null hypothesis because I have no oranges at all, right? So I have only blues. So I simply compute this is number of outcomes as extreme as mine. This is number of outcomes more extreme. And then I take a sum of these two and divide to the total number of outcomes. That gives me the chance, okay? But if I use right hypothesis, this is less likely, right? So that now I expect that the number of blues should be smaller than 50%. But you can see that the number of blues I have, it's 83%. So again, I can compute the p-value how these are all values equally extreme. This is more extreme. This is less extreme. So I take sum of these two and divide the total number of outcomes, and I got a p-value of 11. Right. So this is how it works. And again, this example, this example is good because we can count number of outcomes, so we don't need any distribution. Also, all these events, they follow the binomial distribution, so I can use distribution. But in this case, we can just manually see the p-value, so to speak. We can compute it manually based on the number of outcomes. In reality, number of outcomes is infinite, and that's why we need to use theoretical distribution for computing the p-values. But the idea is the same. When we compute a p-value, it gives us just a chance to get a sample as extreme as we have, assuming that null hypothesis is true, or even more extreme, right? And then, based on this chance, we make a decision.